Hello friends! Now we are going to set up a triple integral and we're going to solve that where we have this triple integral over the solid e of the function square root x squared plus y squared. We want to set this up and determine what our region looks like. E is bounded by y equals x squared plus z squared as well as y equals 4. All right, so what does this solid look like? So we're going to create not the region, but the solid with which we're integrating across. So here's my XYZ plane. What is the graph of y equals x squared plus z squared? We should recognize that as an elliptical or circular paraboloid. And then y equals 4, that's a plane parallel to xz at y equals 4. So that's what's going to cut it off. I'm going to put a little 4 here. And we have a circle. I'm going to draw a circle that's going around that. And then we've got our elliptical paraboloid coming off here. So this is what my surface more or less looks like. I said surface, but that's a solid. Okay, so this is my solid region, and we want to evaluate this integral across this solid region defined by the elliptical paraboloid wrapping around the y-axis and the plane y equals 4, which cuts us off here. All right, now we need to think about how to set this up, and this isn't set up the same way the tetrahedron we did in the last video was. We want to think about what our bounds are. So if we choose first to integrate in terms of z, what are my upper and lower bounds? In terms of z, we would have a function. We'd have to solve this. So if we do first by z, my upper would be z equals the positive square root of y minus x squared. And my lower would be z equals negative square root of y minus x squared. So that's upper and lower. Z in terms of x and y. If my choice was to say I'm going to integrate first in terms of x, I would get something similar, solving this paraboloid to be x equals, I'll have x equals the square root of y minus z squared, and then my lower would be x equals negative square root of y minus z squared. So that would be the front and the back piece, thinking about what we would be touching as we moved out on the x-axis. And then the third option we have for choosing first, if we choose to integrate by y first, then that means we're going in this direction. So my upper and lower y bounds, well, my lower is this solid, and we already have that in terms of y. That'd be y equals x squared plus z squared. And my upper bound, that's going to be y equals 4. That looks weird. All right, so we have 3 choices. So I'm going to choose, I think, maybe that this looks the easiest if I integrate in terms of y. All right, so if I'm going to integrate first in terms of y, then that means my region R, which is going to determine my x and z bounds, that region R is going to be this circle over here in my XZ plane. All right, so that's going to let me determine, how I think about my region. So setting this up, I'm going to have a triple integral, and I don't know if I'm going to do x or z first, but we'll have x and z. And then we're going to have our y bounds. So I'm going to have y equals the paraboloid on the left and y equals 4 on the right. Right? So we've gone from the paraboloid is what we would be touching over here on the left side, and then this plane y equals 4 is what we're touching on the right. Lower left, the upper is on the right side. Just think about how you move on your x and y axis, your greater than and less than. All right, and my function is the square root of x squared plus z squared. So I have that there, square root of x squared plus z squared dy. So now we need to determine if we're going to do x first or z, and what would be the order of that. So what is the region? We said that that region is this shadow. Like if I tilted this, if I turned this 90 degrees over to the left, that would be my shadow below, and that's in the xz plane. And that's a circle of radius 2. We know it's a circle of radius 2 because we were out here at 4. And if I let y equal 4, there's my radius of 2, right? If I find the intersection of these two surfaces. All right, so thinking about this, we have x and z. And this is a circle of radius 2. So that's my region R. So the equation of this circle is x squared plus z squared equals 2 squared or 4. If I want to isolate z, I'm going to have z equals the square root plus or minus 4 minus x squared. So my z bounds, I'm actually going to give myself a little more space. I have z equals negative square root of 4 minus x squared, and then z equals positive square root of 4 minus x squared. So that means dz is next. And then my x's are between negative 2 and positive 2. So I've got x equals negative 2 and x equals positive 2 dx. So that's my setup here. So these last two pieces, those are being formed from my region R. And then the first one I'm finding by looking at that solid. So really, again, we just want to make sure we're focusing on this setup, that we understand how to set this triple integral up. It's not that difficult to evaluate once we have it set up. And in this situation, when we go to evaluate this integral, we're going to end up turning into polar coordinates. So let's do that. Okay, so we want to look at integrating this guy. And what we have here, this is a constant because we want to integrate with respect to y first. So that's going to leave me with y times that quantity, the square root of x squared plus z squared. So we'll plug in 4, we will plug in our function, and now our integrand looks like this: 4 minus x squared plus z squared, and then that coefficient value is still in the front. Okay, well, we're in behind, but regardless, multiplication's commutative. Now, thus, we have to integrate this with respect to z, and there's z's all over the place. This looks like a mess. I know I already mentioned it. Hopefully you guys are thinking about it. Can we convert these x's and z's into polar? And I see a circle here, right? As soon as I saw a circle, we can do this. But what we're going to do, let's think about that region in our xz plane. We have that circle of radius, that's r equals 2 from 0 to 2 pi. Okay, so now we're integrating around a circle of radius 2. So what would that look like? Well, my bounds for theta goes from 0 to 2 pi all the way around the circle. The radius of that circle is 0 to 2. What does my integrand begin to look like? 4 minus, what's x squared plus z squared? That is r squared. And how about the square root of x squared plus z squared? So we've got all of that. That would become times r. Okay, so this guy became that r squared. This becomes r. And since we're dealing with polar, do we need to add anything extra in there? We need that extra r. And then we integrate dr d theta. So if I take this r squared and distribute, I've got 0 to 2 pi, and then I've got the integral from 0 to 2 of 4r squared minus r to the 4th dr d theta. So we took something that was really ugly and we used polar to make it look really nice. So this is pretty simple for us to integrate from here. We got 0 to 2 pi. That will become 4/3 r cubed minus 1/5 r to the 5th. We're going to plug in 2 and 0 and then integrate again with respect to theta. So plugging in 0 doesn't matter. We're going to get 8. 2 cubed is 8 times 4. That is 32 over 3. Minus 2 to the 5th is 32. So I've got 32 over 5. And that simplifies. I've got 64 over 15. So 64 over 15, 0 to 2 pi d theta. That is 64 over 15 theta evaluated from 2 pi to 0, which is 128 over 15 pi. So now we have evaluated a triple integral. We thought about the different ways to set up those bounds, and then we converted to polar in the middle of the integral. So we've got a lot of stuff going on here. I really like this problem, so keep that in mind. All right, good luck out there. Email me with questions, comments, concerns, like and subscribe. Bye.